Welcome to an Introduction to Taylor series. This is one of the most useful approximation techniques in calculus and physics. You'll see we're going to use this all the time. This is named not for Taylor Swift, but for this guy, Brooke Taylor. He was English, and let's take a look at when he lived. He lived from 1685 to 1731, so you can see he was not super old there. What is that? 31 plus 15? 46 years old. Nice bathrobe, Brooke Taylor. And comparing him to Isaac Newton, 1642 to 1726, so you can see there's quite a bit of overlap there. These guys both lived around the time of the invention of calculus, and Brooke Taylor really elaborated on some of Newton's ideas in a very useful way. Let's take a look. This has to do with a question that is near and dear to my heart. How does your calculator actually calculate the sign of a number? This is kind of an interesting question that you might not have thought about. When your calculator is calculating, it can do several things. It can multiply, it can add, it can subtract. These are all things that are relatively simple to do with a really simple computer. It can divide, which is just subtracting several times. Of course, multiplication is just repeated addition, and given that it's relatively easy to multiply several times, if I take a number times itself, times itself, times itself, that's like taking the number to some power, n. So these are all things that the calculator knows how to do, but how would I actually calculate sine when I push this button? How would I do that? Well, we know the sine function looks like this. For some values, this is up to about, say 2 pi over 3. Pi's over here. Function comes down. So what could I do? I could store values and then look them up in a table, but I can enter any number I want here. What if I wanted the sine of 24.93751 degrees? The calculator can still do that. You can give it a try. But how does the calculator actually do this? Well, we need to reduce the problem to just using these operations that the calculator knows how to do, and that will allow us to get any value we want in here at any place along the curve. So let's see how it's done. Here is what Dr. Taylor came up with. So suppose you're given some function f of x. For example, maybe our f of x is cosine of x, and I don't know how to calculate that. I suppose I could actually get the right triangle, and I know that the cosine is, let's see, the adjacent over the hypotenuse. And I could measure these with a ruler, but that's not very convenient if I'm using a calculator. So what else can we do? Well, it would be nice if we had a way to define this function that only used the operations we know how to do, which are addition, subtraction, multiplication, division, and exponentiation, raising to a power. So suppose there's a polynomial that's equal to f of x. We know there isn't a polynomial that's equal to cosine x, but at least there's not one with a finite number of terms. But let's suppose that there was. So suppose this polynomial p of x on the right-hand side here looked like this. I have a constant term, a0, and a linear term, a1 times x, and a quadratic term, a2, x squared, a3, x cubed, a4, x to the fourth. This is what we mean by a polynomial. It's a series of monomials, and generally we either arrange them in order of decreasing power or in order of increasing power from the constant term up to who knows how many terms we have here. Maybe we have an infinite number of terms, but let's check it out. So I know if f of x is equal to p of x, then they are equal to each other for every value on the function. But also, if f of x looks like this, here's cosine, and p of x looks like this, it's also, well, they must be equal even though it's a polynomial. These keep going forever. What that means is if the slope here is some value, it must be the same value here. So not only is the function's value the same for f and p, but the slope must be the same at every value, and the curvature must be the same at every value. And the hypercurvature, the rate of change of curvature, must be the same at every value. So it would be nice if we could figure out how does this function p of x relate to the first and second and third and fourth and all the derivatives of this function f of x. Let's see how that happens. Well, is there something I could do that would tell me what a0 is? Well, what happens if I evaluate this function f of x at x equals 0? Then I have times 0 squared times 0 cubed times 0 to the fourth. And I know 0 to any power is going to give me 0, so all these terms are 0. But here I just get a0. I know f of 0 must be a0. So because what I'm interested in is a0, I know that a0 then equals f of 0. And that's a fact I want to remember. Now looking at our function, remember we know already that f of 0, that's how we get a0. But what if I wanted to know what a1 was? Well, let's take the derivative. F prime of x is equal to, well, the derivative of a constant is just 0, and the derivative of this linear function, this is x to the 1, I bring down the exponent multiplying by it, so I have 1 times a1 x to the 0, which is just 1. So that's 1a1 plus, taking the derivative, I have 2a2 plus x0. Sorry, 2a2 times x to the 1. The rule is lower the power by 1 and multiply by that what the power used to be. So I have 2a2 times x plus, what happens here? 3a3 times x squared. Well, what happens when I plug in 0? Here, I'm going to get 0 and 0, so these terms will go away. So this tells me that f prime of 0 is equal to a1. So let's note what a1 is here. a1 is f prime of 0. But moving on, now we have found a0 and a1. I'd like to know what a2 is. Maybe it's f prime prime of 0. Let's see. Well, the derivative of the derivative, let's write a few more terms here. Here's the first derivative. I have 1a1 plus 2a2 times x to the 1 plus 3a3 x to the 2 plus, we bring down the 4 here, 4a4 x to the 4 minus 1 is 3, and of course we're going to have 5a5 x to the 5 minus 1 is 4. So what happens when I take the second derivative? We used this fact already here. F prime of 0 is a1. So let's clear up some space. I know that f prime prime is just the derivative of f prime. So the derivative of this constant a1 is just 0. Now the derivative here, this is x to the 1, so I have 2a2 plus, bring the exponent down, so I have 3 times 2 times a3 times x, and here I bring the exponent down, so I have 4 times 3 times a4 x squared plus 5 times 4, I'm going to bring down that 4, 5 times 4 a5 x to the, we lower the exponent by 1, 3, so I have constant, linear, quadratic, cubic, and of course there's plus dot 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 on both of these. So f prime prime of x is all of these terms, but notice still if I plug in x equals 0, this term, and this term will be 0. So that tells me that f prime prime of 0 is 2a2. Or, conversely, a2 is f prime prime of 0 over 2. So we see a2 is f prime prime of 0 divided by 2. we've used this evaluation at 0 to find that out. Let's clear out some space and take one more derivative. So f triple prime of x is, derivative of a constant is, you guessed it, 0. I bring down the 1 here, so I have 3 times 2 times 1. Hey, that looks like a pattern. Times a3, x to the 0 is 1, plus 4 times 3 times, bring down the 2, 4 times 3 times 2, times a4, now I lower the power by 1, that's my power rule, x to the 1, plus 5 times 4 times, I bring down this 3, you see the pattern here, times a sub 5, x to the, lower the power by 1, 2. So I have constant, linear, quadratic. Of course, there are more terms. But have you noticed what we always do to find the value of these coefficients is we plug in 0 for x, because that'll get rid of all these x raised to a power. So f triple prime of 0, what is it? This term sticks around. These all involve 0 to raised to a power. That's a 5. So I have 3 times 2 times 1, a3. So what does that mean? A sub 3 is f triple prime, 3, triple, that matches, of 0, divided by 3 times 2 times 1. I notice 2 is also 2 times 1. So this is a sub 3 up here. Let's give ourselves a little separation. A sub 3 is f triple prime divided by 3 times 2 times 1. That's evaluated at 0. And I think we're catching on to the pattern. Let's take one more derivative. The fourth derivative is the derivative of the third derivative. So, clearing out here our substitution of 0 into the value, I see that derivative of a constant, of course, is 0. And I have 4 times 3 times 2 times 1, a to the fourth. That's pretty clear evidence for me. 4 times 3 times 2 times 1, a to the fourth, sorry, a sub 4, and x to the 1 becomes x to the 0, which is just 1. So that means that a sub 4 is, don't forget we're evaluating this at x equals 0, a sub 4 is f fourth derivative evaluated at 0 divided by 4 times 3 times 2 times 1. Now that looks clear enough to me to see that a sub n, the nth coefficient in this polynomial, is just going to be f, the nth derivative, evaluated at 0 divided by n factorial. So that is a pretty great trick. This tells me a way to find these coefficients so that I can rewrite any function I want, as long as I can take its derivatives, as a polynomial. So that's what our calculator wants. This is a way to calculate, say, cosine or sine just using a polynomial. Let's try that as an example. So suppose f of x is cosine of x. Then what is f prime of x? I know the derivative of cosine is negative sine. If I don't know that, I can look in the inside cover of my calculus textbook or in a table of derivatives anywhere I want. It's a famous result. F double prime of x, derivative of negative sine of x, is negative cosine of x. F triple prime is sine of x. And the fourth derivative here is derivative of sine is cosine. Now, what this means, since I got back to the function itself, is every time I take 4 derivatives of this function, I'm going to get back to the function itself. So let's use those to evaluate this function at 0. So f of 0, cosine of 0 is 1. F prime of 0, negative sine of 0 is 0. F double prime of 0 is negative cosine of 0, so that's negative 1. F triple prime of 0 is, that's sine of 0, which we know is 0. And f fourth derivative, evaluated at 0, is going to be cosine of 0, which we know is 1. So this pattern 1, 0, negative 1, 0, 1, 0, negative 1, 0, that's going to continue forever. So what does this mean that our Taylor series will be for cosine? Well, let's give it the plug-in treatment. So that means that f of x will be a0. I know that f of 0 is a0, so that's 1. My first derivative is 0, so I'll skip this linear term and go to the quadratic term. a2 is going to be, remember, f prime prime divided by 2, because it's 2 factorial. So that's plus negative 1 over 2 factorial times x squared. Now the third derivative is 0. a3 is 0, so I'll move to the fourth coefficient. The fourth coefficient is the fourth derivative, so that's going to be a plus positive 1 over 4 factorial, and this is the coefficient of x to the fourth. I know all my odd numbered terms are going to be 0, and when I take the sixth derivative, I'll have 4, 5, 6, gives me a negative again, so I have negative 1 over 6 factorial, x to the sixth. So I've got plus, minus, the next one will be plus, and 1 over 8 factorial, x to the eighth, plus dot dot dot. So you see the pattern. This is going to be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus x to the eighth over 8 factorial. So I've got the even numbers here, factorial in the denominator and also in the exponents, and we're going positive, negative, positive, negative, positive, etc. So does this actually work? Our claim is that this is equal to cosine. Can you believe that? Well, let's check it out.